And to finish off these videos by looking at types of sequence and then some things on sigma notation. So first of all, a sequence is said to be increasing if. Now I'll read this out as it's written and then we'll write down some explanations. So the next term in the sequence is greater than the previous term for all values of n which belong to the natural numbers. So mathematicians use this notation, the upside down a, which means for all, and the sort of elongated e means belonging to, and n is simply the set of natural numbers. And it's just a nice way that we have of neatly writing down that this is always the case, that it's always for n belonging to the natural numbers, so for any value of n. So for any term, n plus 1 is always greater than its predecessor. Now, unsurprisingly, a sequence is decreasing if the next term is less than its predecessor for all values of n which belong to the natural numbers. We also get these interesting things called periodic sequences. So a sequence is periodic of order k if, now new notation, so we say there exists a k such that some term later is equal to a previous term for all n belonging to the natural numbers. So our new thing here is this thing, which means there exists. Now this is best seen by talking about a geometric sequence. So let's talk about a geometric sequence with a of 3, and let's say that r is minus 1. Where's my 3 gone? Now in this case the sequence would read 3 minus 3, 3 minus 3. So we can see that the terms are the same, just 2 further down. So we would say that this sequence is periodic of order 2, because the terms take 2 sort of turns before they repeat. We've also talked about divergent series. So a series is said to be divergent if its values escape towards infinity or minus infinity as we head towards infinity. We've also talked about convergent series. So again, there exists a k such that that series will converge to that value as n tends towards infinity. We've seen that again with geometric series, where we know that the rule for that is that the infinite sum is going to be a over 1 minus r, provided that r lies in this sort of Goldilocks region between minus 1 and 1. Let's move on now and look at sigma notation. So you may have come across sigma before. So sigma is written lowercase as this and uppercase as this. Lowercase, we tend to use it in statistics to talk about standard deviation. Uppercase, it's always used to signify a summation. In this case, it's the summation from k being 1 to 5. So we then just run through. So we say, well, k is 1. That would become 3 times 1, which is 3, plus 1, which is 4. Plus the next term when k is 2, this becomes 7. When k is 3, this becomes 10. When k is 4, this becomes 13. And when k is 5, this becomes 16. So another way of writing this down is to write it out in its longer format, I suppose, as this. And the answer to this would then just be 50. In a similar way, here we have the sum again from k is 1 to 3 of 2 times k to the power 3 to the power of k. Substituting in my values, that becomes 6 plus 18 plus 57, and that gives me a total of 78. So this sigma notation is just used as a shorthand rather than writing out a series of values. We've got a couple of special results. If I add together 1 any number of times, so n number of times, then what do I get? Well, I just get n. If I add 1 together twice, I get 2. If I add 1 together 3 times, I get 3. If I add 1 together 10 times, I get 10. So the sum from 1 to n of 1 is n. The sum from 1 to n of k, well, what does this look like? Well, that would be 1 plus 2 plus 3 plus all the way on until we get to n. Now, we can think of this as being an arithmetic progression because its first term is 1 and its constant difference is also 1. We have a formula that allows us to find the sum of this. It's n over 2 lots of 2a plus n minus 1 lots of the difference, which is n over 2 lots of 2 plus n minus 1, or tidied up, that's n over 2 lots of n plus 1, and I don't know why I've written down n here, it should be equals. Again, we could have got there much faster by remembering that the alternate version of this formula is that it's the first term plus the last term. So it's n over 2, lots of the first term plus the last term, and that just gives us the sum of the natural numbers, which again is quite a nice result for us to use. Next up, we're going to look at how we write things into sigma notation. So we can see here that we've got a constant difference in first value 5, so a is equal to 5, and the constant difference here is 2. So this becomes the sum from k equals 1 to, I've got 5 terms here, of 5 plus k minus 1 lots of 2. So k is just my placeholder. Pen's really not liking me. And I can expand that and simplify, so this becomes the sum from k equals 1, again, pen not liking me, to 5. Expanding that is then going to give me 3 plus 2k. And that's how I would write down this sum. I can find values for these things, so here I'm looking to add up the numbers between 1 and infinity of this, which is just a shorthand geometric series, and if we can't see that, we would always want to write out the first few terms to sort of get the hang of what's going on. So the first term's 4, then the second term of this is going to be 4 times a fifth, and then the next term is going to be 4 times a fifth squared, and so on. So we can see that a is equal to 4, and we can see that the common ratio is 1/5. And importantly, I know that's less than 1, so I can now use my sum to infinity being a over 1 minus r, which would be 4 over 1 minus a fifth. 1 minus a fifth is 4/5, so that's 4 divided by 4/5, which is 5. So if we translate it out of the sigma notation, we can see better what it is, and then we can apply our mathematics to that. The last thing I'll show you are these Trixie questions where the base number is not 1. Now we always have the same way of dealing with these, and that's to say that if I'm to add all of the numbers between 6 and 10, that would be the same as adding all of the things between 1 and 10, and then getting rid of all of the things between 1 and 5. Now we always use the same trick because our sums always have to start at 1. They will throw these things in there to try and catch you out, but I want to do the sum to 10, take away the sum to 5. Now again, this is a geometric progression, and I know that the sum of a geometric series is going to be a lots of 1 minus r to the n all over 1 minus r. So this becomes the sum to 10, so that's going to be 4 lots of 1 minus 3 to the power of 10 all over 1 minus r, which is 1 minus 3, minus 4 lots of 1 minus 3 to the power of 5 all over 1 minus 3. I can then write this all over minus 2. Expanding the first bracket, that's 4 minus 4 times by 3 to the power of 10 minus 4 times 1, which is just 4, so we'll get rid of that bit, and then minus that makes plus 4 times by 3 to the power of 5. So perhaps a neater way of writing this down before I put it onto my calculator, because the 4's are going to cancel out. I'm going to have 4 lots of 3 to the power of 5 minus 4 lots of 3 to the power of 10 all over minus 2. And again, we could go through and tidy this up even further. If I divide all of those through by that negative 2, that's going to give me minus 2 lots of 3 to the power of 5 plus 2 lots of 3 to the power of 10. At that point, you really do have to resort to a calculator, and you are told that the result is 117,612. The important factor to remember that where we've got sums that don't start from 1, we always have to split them. So I've split up here the sum to 1 and 10 minus the sum to 1 to 5 is only going to leave me those values 6, 7, 8, 9, 10, and that's it.